Welcome to week 5, everyone. We have an exciting week ahead of us, mostly because there's so many new faces in this room. It's wonderful. A lot of you are here by accident, which is even better. So hopefully you'll keep joining us. This week, we're going to spend the bulk of section preparing for the quiz. So per our agenda, we're going to talk a bit about resources for the class, but also for the quiz. And then, again, spend the bulk of class talking about questions. Once we're done answering your questions, or if your questions naturally lead us to some coding, I have sample problems from midterms past that we will code live in section together that also bring up some other good topics to cover. So first, as we've gone through for the past couple of weeks, to remind you guys, there are a ton of resources available for this course. Many of them will be incredibly helpful to you as you continue to study for Quiz Zero, because it's Tuesday afternoon, so all of you have been studying for a bit. There are lecture notes and source code that you should definitely check out. Watch the shorts, check out study.cs50.net, and then listed below a number of other resources. Again, Quiz Zero is tomorrow at 1 o'clock. If you haven't done so already, check out the About Quiz Zero document on the course's homepage to figure out where you're taking the quiz. The quiz starts at 1:10 and ends 70 minutes later. So if you show up after 1:10, you're going to get that many fewer minutes than 70 to take the quiz. So make sure you're there on time. If you're an extension student or have some other testing considerations, it might not be at 1 o'clock tomorrow. But again, check the About Quiz Zero document to make sure you know when you're taking the quiz. I wrote 75 minutes up here. I think that's right, not 70. It covers all the material from week 0 to last week's lecture on Wednesday. And again, for this quiz, per that document, you get one two-sided 8.5 by 11 sheet of paper that you get to use as notes during the quiz. Many people, if not most people, have found that the single most helpful way to study for the quiz is to make a study sheet, a one-sider of their own. So look at past ones. If you've seen past ones, reach out to friends to see what they're putting on theirs. But hands down, the best way you can study is to go through everything and whittle it down to what should or should not belong on that sheet of paper, because that's just a really helpful way for you to make sure you're going through everything and have some familiarity with it. Most people, we find, even though they have the sheet of paper sitting right next to them on the quiz, don't turn to it. Because, again, that very process of going through the information has helped them learn it. Does anybody have any questions about Quiz Zero? Has everybody, I'm not going to do a show of hands. Never mind. I was going to ask who started studying, but I don't want to make you all not raise your hands. So, like I said, yes, Avi, go ahead.
What would be a useful thing to put on the one-pager?
It's up to you.
You get to use your judgment. Useful things to put on the one-pager, if you are confused about the big O runtime of different types of searches and sorts, put that on there in a handy-dandy chart. That way, if you're asked that on the quiz, you don't need to try and figure it out or reason through the runtime. You can just copy it down. If you look at quizzes past, a lot of times there's running time questions. So that would be an example of a good thing to put on the quiz, or on the hand, or your one pager. Other good things to put on, if you're confused about how to declare a function or what the different parts of a function declaration are, write that on there, a generic version and then maybe an example. If you're confused about pointers, a diagram of how pointers work is probably really helpful. If you're confused about recursion, a sample recursive function on there could also prove to be really helpful. Does that give you some ideas?
Understand the entire compiling process, like how that all works?
Everything that has been covered could show up on the quiz. Questions, but again, some things will be weighted heavily than others. Some things have come up again and again in class, in lecture, and in section. Other things have not come up that often. We've talked a lot about sharp include and -L something and what those mean in the compilation process. We've talked a lot about GDB, Clang, those different flags that we use when we compile something, and what a make 15, for example, really means and really does. We have not talked as much about every single step in the compilation process. We've still talked about it, so it's still something that you should be familiar with. But again, we're not going to be, things that come up more often in class are more likely to come up more often and be more heavily weighted on the quiz. Cool. Any other questions about Quiz Zero? OK, so I put a list of topics on the board. I went through the syllabus. I went through the review section, or the review section from last night and those slides to come up with a non-exhaustive list of topics that we have covered so far in CS50 and things that might appear on the quiz. So I'm not going to go through every single one of these. That would take much more time than we have now. But I put this up here to hopefully jog your memory as to things that may or may not be as familiar with you. And I'd love to spend the bulk of section answering your questions about these topics, topics that aren't covered here. We can write pseudocode. We can write real code to ensure that I can answer your question and help everybody fundamentally understand a lot of these topics so you'll feel prepared and comfortable going into the quiz tomorrow. So read over the list. You hopefully have come to section with some questions as well. When you're ready, raise your hand, and we will get started. Keep in mind, the questions you have, there are no stupid questions. We've heard that a lot. And the questions you have, I am willing to bet many other people, both sitting here and watching online, have as well. So you can only help people by asking questions. Marcus.
Between the stack and the heap, is there a pre-allocated percentage of memory that's defined as this is for the stack or for the heap, or how does that work exactly?
Great question. I'm going to backtrace a little bit. Does everybody, please be honest here. I know I'm asking you to raise your hand in front of your peers, but does everybody are there people who feel uncomfortable with the stack and the heap and would like to go over that and what those mean? Raise your hand. Okay, thank you. So we're going to go over the stack and the heap really quickly and then move into answering your question. So if we draw out a box to represent memory on your computer, what are some things that go in this box? Main. A main function. Where does main go? Okay, so we'll put main down here. What else goes in this box?
The functions that you call.
The functions that we call, and where do they go?
In the stack.
They go in the stack. So we're going to call this thing down here the stack. And up top, we have the heap. So memory is not a box just like this, but it is actually pretty similar. It's going to be a lot of boxes over and over, depending on how big your computer is or how big your memory is. At the quote-unquote bottom is the stack. And there are multiple things that go on the stack, and those depend on the functions you have in your code. You always have one function in your code called main, so there's always a section down here in the stack devoted to main. These sections in the stack are called stack frames. When you call another function, say main calls a binary search function, we put another frame on the stack, and in more specifically, we are going to donate a chunk of memory on our computer to store binary search's local variables and to run the binary search code. So we call binary search. In this chunk of memory, we're going to store its local variables. We're going to store its printf calls. Whatever happens at a function is going to be stored right there. Binary search is going to execute. It is going to complete execution. What is the word in C that signifies that a function should complete its execution?
Return.
Return. So whenever you see a return statement, the function ends when it hits that. So binary search will hit its return. This part of memory will essentially be freed up, and main will go back to execution. So main will pause wherever it was, call binary search, get some return value, and continue execution. This stack frame will go away. If we call a recursive function, which is a function that calls itself over and over, we might get, say we did binary search recursively, we might get binary search version 1, binary search 2, binary search 3, binary search 4, binary search 5, and then this final binary search 5 will hit the base case, and the stack frames will go back and keep closing until we get back to main. We can go over recursion in a bit, but all this is to say if you're calling multiple functions at a time, there'll be multiple stack frames on the stack. The heap, on the other hand, up here, is not for functions, not for local variables. It's for it's for dynamically allocated variables. So these are variables that can be initialized in either main or a function that main calls. Anywhere in your code, they can be initialized. And to initialize a dynamically allocated variable, what function in C do we use? Malloc. You call malloc, you get a space of memory, and that space of memory is on the heap. And that space of memory stays there until you call free. So dynamically allocated variables in the heap will exist for as long as you want them to exist, and they won't go away until you explicitly tell them to go away. You can create them in one function. That function stack frame will go away, but that variable will still exist in the heap until it is freed, potentially by the function that called binary search or whatever. So those heap variables stay there for as long as you want them to stay there. And they get put here, and then the next one gets put there. They keep getting filled in, and they stay there until you call free. And essentially, the heap and the stack, getting to Marcus's question, grow towards each other. And if they run into one another, you've used up all the memory in your computer, and your program will quit because you don't have any more memory left to use. In between them, there are potentially other things, but for the scope of this course, you don't need to worry about that. Okay. So that was the answer to your question. Don't worry about it. But that was the long answer. All you need to know is the heap and the stack will, one starts at the bottom, the stack does, the heap's up there. They will grow closer to one another, and if they touch, that's a problem, you ran out of memory. But also, in addition to knowing where they are, what is stored in both the stack and the heap. Curtis.
And when they collide, is that Stack Overflow?
When they collide, that's not a Stack
That's
Overflow.
not a Stack Overflow.
A Stack Overflow is a different area that we can go over if you want to.
Yes, I do want to.
Okay, we'll come back to that in a bit.
What's the error called when they hit each other? The stack and the heap?
For now, don't worry about that. Just know, I will answer that question after class. If they run into each other, you ran out of memory because there's no more space there.
Sorry, what's a seg fault then?
A segment fault can be called for, it depends what a seg fault's called. If you see, sometimes your Stack Overflow, it'll say seg fault as the error.
What about dereferencing a null variable? What is that a seg fault?
Dereferencing a null pointer. Okay, so if you have a pointer that you set equal to null, pointers recall store memory addresses as their values, and a null pointer is essentially storing 0, the 0th address in that variable. So 0x0000, etc. That 0th address in memory, that's not in our picture. That's up there somewhere. That's reserved for the computer. We're not allowed to touch it. So when your program's executing, if something is trying to go to memory address 0, it knows that that is like an empty value. It knows nothing should be there. So if you try and use something there and treat something like there, try and go to that location, you're going to get a seg fault or an error. Does that answer your question? And we'll go back to Stack Overflow. Things in the stack, as you guys have seen before. Let's draw a close-up of a stack frame. Can everybody see that? OK, so we have our stack frame. We're saving an array as a local variable in this function. So say our array has 5 spots. All 5 of those will be stored in that stack frame. If we start writing beyond the bounds of this array, so if we start writing into, let's say that's 0. Those are the 5 indexes of our array. If we start writing into index 5, which we don't have when we have an array of size 5, we start writing into index 6, 7, 8, 9, we can get a Stack Overflow error. Generally, it's not, you will probably get into trouble if you go over by 1. But generally, you will get into the most trouble if you go over by a lot. And you go so far over that you write over the return address of that function, which is located at the bottom of the stack frame. Because in the stack frame, you have your local variables. At the very bottom of the stack frame is the return address. That's where that function goes when it's over. And if you overwrite that return address, then when you're going through the stack frame and executing each line, you're going to go to your new return address that's written there instead of the actual one, and that's how we've seen some security breaches can happen with computers. So Stack Overflow, in short, is when you overwrite the part in the stack that you're supposed to use, the local variable you're supposed to use, and in particular when you start overwriting important things like the return address. and that's where you'll get an error. Or maybe even you could start even writing into, say binary search was right above main. If you overwrote a lot, you could write into main. But generally, you'll get an error before then because the computer knows you're doing something you shouldn't be doing. Yeah?
What's the difference between a stack overflow and a buffer overflow?
A buffer overflow is a more generic type of what I just described.
So stack overflow is an example of a buffer overflow.
Exactly. This is an array we can think of as a buffer, a space for things to go in. This is a stack buffer overflow. We could have a heap buffer overflow. If there was a buffer, which there often is, an array on the heap, and we overwrote those bounds, then we would have a heap buffer overflow. And beyond the scope of this course, they're detected a bit differently. The compiler has special ways of detecting each. But a buffer overflow is a more generic type of what I described, which was a stack buffer overflow. Did that answer your question? Yes. Sweet. Were there any other questions related to the stack or the heap? Yeah.
I know you have to free strings because they're in the heap and you don't want to leak memory, but do you have to free like global variables and stuff like that? Or are they automatically freed?
Good question. So a string in CS50.h, we create this thing for you called a string. A string is really what? A char star. A pointer to a character, a pointer to an array of characters. That's what the string is. So we need to free it because getString, which we've used a lot, string name equals getString, that mallocs for us some memory on the heap and then returns a pointer to the first character of that string, a char star. So we need to free, ostensibly, if you have not been writing free on any of your strings that you've called so far, you have been leaking some memory. Of course, we haven't talked about it, so nobody's gotten in trouble for doing it. But going forward, yes, when you call getString, you're mallocing some space on the heap. And if you don't call free later on that string, you have a memory leak. Does that answer your question? Yeah.
So we do that. We use free like right before return, in like within the scope of, I guess if we say like int main, within the scope of the whole like function. I mean within the scope of the code that's within those curly braces. Right before, you know where you'd usually put return, do you put free before that?
So you can put free wherever you want to put free. It doesn't need to be, because these are dynamically allocated variables, because they can live beyond the scope of a particular function, if you call malloc in a separate function, for example, getString, you can call free in main. You don't need to call it in the specific function where malloc is called, but you do need to call it before main returns. And it really depends. It depends on why you malloced that space in the first place. Some people will call free pretty quickly. Some people will call free till the end of their program, and they'll go through and free everything. It depends on why you called malloc.
And what would you say if you were like, if you called, if you, I guess, used getString, you'd say free what?
So if you have the syntax for free is simply free, open paren, close paren, and the name of the pointer. So if you write string name equals getString, you put name in here. That's the name of the pointer, and it knows to free that memory. Mm-hmm.
So when it frees that memory, does the pointer still point to that place in the memory? Or is the pointer also like emptied of the address that it points to?
We should try that. We should code that.
Okay.
Let's come back when we get to coding and let's code that.
Okay.
And if you want to figure out the answer to that, you could also code that in the meantime.
Right.
But it's a great question.
Okay.
Is it possible to free something too soon? Like you still need it for your program and you freed that memory space?
Yes, it is possible. If you free something and then you use it again, you will run into an error. But that's on you because you freed something and then called it later. So that was a programmer's mistake. But yes, you could write that. Mm-hmm. Any more questions on, yes?
So if you are supposed to just free it in general before the program ends, does that mean if the program ends and you don't free it, that memory is still allocated?
If your program ends and you forget to free something, then that memory was allocated throughout the lifetime of your program. Mm-hmm. When your program closes completely, that memory is not going to stay there forever. Okay. The computer is smart enough to know that when the program closes, it should get rid of all of the memory that was associated with that program. However, there are tools you can run on a program to detect if, when the program finished, you forgot to free some memory. And for your next problem set where you will be using malloc and using pointers, you will be running this program on your program to see if when main returns you had some things that were left unfreed. So they're not going to stay malloc forever on your computer. That would be wasteful because very quickly computers would run out of memory. But they do, if they run till the end of your program and they're not freed and your program exits, that's still a problem that this tool will help you address.
Okay. Is that Valgrind?
It's called Valgrind, and you'll be...
So we don't have to know that for the quiz, though? I mean, it was talked about a little bit in lecture, but...
So I didn't say Valgrind is the name of that tool. You knowing what it does is enough for the quiz.
Okay.
But you have not used it yet on your problem set because we haven't had a problem set that has explicitly dealt with malloc or you using malloc. So you haven't used Valgrind yet. But you will use it sooner rather than later.
What Valgrind is?
Sorry?
Can you repeat what the purpose of Valgrind is?
Valgrind is the name, like GDB helps you debug your program. Valgrind helps you figure out if things have not been freed when your program closes. So you'll run it on your program, and your program exits, and it'll say, your program called malloc this many times for this many bytes, and you only called free this many times. And so you left these many bytes without being freed. Or it'll say, you freed everything, good job.
Okay, and it's spelled Valgrind.
Valgrind.
Question about pointers. So say you have like int star x equals something, right?
Mm-hmm.
That equals whatever you're putting there. Is that what's being put inside what x is pointing to, or the pointer of x?
Can you repeat the question?
So like, okay,
Can we draw it while you say it? Okay.
Okay, in the quiz actually, it like the one you sent us, it was like char star truth equals CS50 rocks, right? So does that mean that like that CS50 rocks is what the truth is pointing to?
So you're talking about a string, a char star and a string?
Yeah.
How that works?
Yeah.
Okay. Let's draw this over here.
What is going to go inside the address that truth is
Pointing to.
because it's a dereference pointer.
But this is a declaration.
So this variable is going to be of type char star. How big is a variable of type char star? How many bytes?
Four.
It's 4 bytes. How many bytes is a variable of type int star? 4 bytes. A pointer, if it's a pointer, then it is always 4 bytes because pointers, their value is a memory address. And memory addresses on the CS50 appliance are 4 bytes long. So when we call getString, or when we say string name equals and then in double quotes put a string, we are putting, well, that's a little different. We'll do getString as the example, or char star something equals the string. Sorry, give me the example you read.
Yeah, like char star truth equals CS50 rocks. Like
Okay.
double quotes.
So this star, we'll call this variable x for our generic purposes. We created a variable called x. It's type char star. It is a pointer to a series of characters. So down here, so this is how this would work in memory. This would store a memory address. It would store the memory address of the first character in the array. And then when you followed the pointer, you would get the first character. And if you're reading this thing like a string, your computer is smart enough to know, read this whole thing until it gets to a \0. But if you're reading it a character at a time, say you're iterating through this string, then you will just read a character at a time until you get to the \0. That might not answer your question, though.
Yeah, but like you haven't malloced like that space yet for that pointer.
So that I'm not quite sure exactly what you're looking at because I didn't make that quiz. That was supposed to be a helpful resource from another TF. If you were creating a string on the stack or as a local variable, it'll just be an array of chars rather than generally a char star pointing to another string. But it could be, you could also be, I don't know, that could be a pointer to another string on the stack as well. Yeah.
Maybe I know that you need to allocate memory if the pointer is being declared inside of another function. Do you need to do the same thing if it's being declared inside of main and you're using it inside of main?
Okay, so if you declare a pointer, yes, you can declare a pointer to any memory address in memory. It can be the memory address of a local variable, though oftentimes people don't declare memory addresses to local variables because they go away once that function returns. which is why we generally malloc things. But yes, you could declare a pointer to another local variable. That's just generally not done.
Yeah.
But I can take a look at that specific thing after class. Yeah.
I mean, yeah, it does. I think this is sort of what is being asked. It does seem strange to be initializing a pointer not as an address, but as like what seems like a value, right? It seems like the CS50 is what's inside the thing being pointed to, and not the actual address, right?
Okay. Yeah. So that's not the case, though. That's not what's happening.
Okay.
When you declare a char star, it's a memory address. Pointers are all memory addresses pointing to something else. That something else could be on the stack, but almost always is on the heap in the way we will see it used.
Okay.
But yes, you wouldn't but string name equals double quote get string. We can see that and we can look through that and code that. Get string is not being saved in that variable. That's not, or whatever the string name is not being saved in that variable because that's not how pointers work.
Right.
Does that make sense?
Yeah.
Okay. Hopefully that wasn't confusing to anyone. But if it was, we can look at it again in a bit because we're actually going to code something that will hopefully work with strings and help you feel more comfortable with them. Okay, any other questions related to these topics or other topics that I'll put back up? Right now. Yes, Alden.
So this is completely unrelated, but can we just go over really quickly what we need to know about the difference between a 32 and 64-bit machine?
Yes. So, 32 bits is how many bytes?
It's 4 bytes.
Is 4 bytes. And 64 bits is how many bytes?
8.
8 bytes. So again, 8 bits is 1 byte. Your CS50 appliance is a 32-bit machine. So memory addresses are 4 bytes long. There are 2 to the 32 memory addresses, 0 to 2 to the 32 minus 1. And I am not positive, but that's probably the scope of what you need to know for a 32-bit machine. That memory addresses are, again, 4 bytes long, and that's the maximum amount of memory addresses. Also, data types. This might be something as well that's worth noting. Data types, the size of a data type depends on the machine you're working with. So a char, a single character, is how many bytes on our CS50 appliance? 1 byte. And it's actually 1 byte as well on a 64-bit machine. And most data types are the same number of bytes on both machines, but some data types will be different on both machines. So that would be potentially the only thing you need to know, but even that I think is beyond the bounds. I'm almost positive if you look back at old quizzes, it says assume for coding problems, you're using a 32-bit machine.
Okay.
So, but there are, to go along with that, in case you're interested, there are data types that are the same size on all machines. They are, if you've seen something like uint32 underscore t, you may or may not have seen that. That's a data type that is saying be 32 bits no matter what machine this is on. So when people are writing portable code, they probably won't use ints. They'll instead use these other data types that they know will be the same size on every single machine. Madhu.
I have a question about the compilation process. So
Okay.
if you're writing a program that uses a library like CS50 or something like that, I know that library has to at some point be like compiled and linked in.
Okay.
But at how much of that happens during the compilation of your program? Like what part of that library process occurs when you're compiling your own program?
Okay. So let's go over in generally the steps of this process. You write your .c file. In your .c file, you sharp include your header libraries. For example, cs50.h. What does that sharp include line do to your program? Akshar.
It adds the prototypes of the functions from the header files in the libraries.
Exactly. It adds the prototypes, those function prototypes, to your code. So when your code is being compiled, in the early stages, the compiler knows that these functions really exist. and that somewhere they have been defined. The .h files don't include the definitions for these functions or how they actually work. CS50.h just includes something that says getString is a real thing that can happen. And standardio.h says printf is a real thing that can happen. So your C language with this .header file gets turned into some machine readable code, which eventually gets turned into binary code, zeros and ones, and that's the code that ultimately gets executed. The -L CS50 line, for example, when you're writing Clang, and then you include -L CS50, you type that in, and you see that when you write make, you'll see that line appear, and we'll see that in a second when we code, or later on when we code. But that -L CS50 line does something a bit different than the sharp include CS50.h. What does that -L CS50 line do? Avi?
I want to say that it links the library to the function call, like the .o files.
So very close. The -L, yeah, if not spot on. The -L CS50 takes the binary file and merges it with your binary file. So CS50.h, there's no point in turning CS50.h from C language to binary every single time it's being used. That would be silly, because that would waste a lot of time. So it has already been compiled and turned into an executable, and that is going to be merged with your file at the end. So you have those ones and zeros are going to be merged with your ones and zeros at the end. So now you'll actually have the actual ones and zeros that define how getString, for example, works, or how printf, for example, works. And for more information, there's a short on compilers that Nate gives that you should check out that goes through these steps. But yes?
Are they always in .o files when they're like in the library form? Like ready to be, I guess, merged, linked, like they're in the binary code?
Okay. What?
Like, is that always the case for the libraries when you link them?
Yes. So they're different. There's .s files, which will be machine code, which will also be cryptic to you. You don't need to worry about those. But generally, yeah, they'll be in .o files ready to go.
So when you ship like a library, do you only ship like the .h and the .o? You don't ship the .c or the .s?
Okay, so this is in the short as well, if this information seems to be coming a little quickly, but the short on compilers talks about this as well. When you ship a library, if you ship the .h, the header file, those function prototypes, and the ones and zeros, that's all you need to give. You don't need to give how the function works, the .c file, because the point of abstraction, or the point of APIs, the point of the SPL, the Stanford Portable Library, is for you to not worry about how NewGrect works, or how move works, or how add works. All you need to know is that add is a function that you can use, and it does this. So you really don't need to know how it's written in C. You just need to know here are the functions, what they do, and here are the ones and zeros when you really want to use them. Cool. Any more questions on compilers or other topics on the board?
I have a question about implementing recursive functions.
A question about recursion. I had a feeling that would come up. So let's quickly go through recursion with a specific example, a factorial function, because this is an example that often comes up or is used to illustrate recursion. Oh. So 4 exclamation point is read as 4 factorial. And what does 4 factorial mean? What does that do? How do you calculate 4 factorial? 4 times 3 times 2 times 1. So another way to write 4 factorial is to write this. 4 times 3 factorial. Because 3 factorial is 3 times 2 times 1. So 4 times 3 factorial is 4 times 3 times 2 times 1. This is why factorial is a great candidate for recursion, because it's clear that there is something that happens over and over and over on a smaller number of things until you reach the end. When you reach 1, 1 factorial is 1. You can't go much further. 0 factorial is also defined as 1. So when you get to 1 or 0, you're at the end and you can start going back up. So we're going to write, if we wanted to write a recursive function to calculate a factorial. We're going to write some pseudocode for that now. Before we write that pseudocode, I'll give you guys a couple of minutes to write the pseudocode, or just think about it. There are two things every recursive function needs. What are those two things?
It's to call it.
Noah? Oh, Jeff, go ahead.
It has to call itself.
So a recursive function needs a recursive call, a call to itself. That's one. And what's the other thing?
A base case.
A base case. A base case is, here's when we stop. So your function gets called. The base case comes first. You want to know if you're at the end. And if you're not at the end, you make your recursive call. And you go through this function again, check your base case again. If you're not at the end, you make another recursive call, et cetera, et cetera. That's why recursive functions always need those base cases and those recursive calls. If you didn't have a recursive call, it wouldn't be a recursive function. If you didn't have a base case, you would go forever and there would be no ending. And the base case always comes first because you will always want to check if you're at the end first. So before we do some pseudocode, why don't you take a minute to think about how a recursive factorial function would be written. Also, as many of you are doing, writing it out on a sheet of paper is what you're going to have to do on the quiz tomorrow. So probably good practice to make sure the code you're writing down on sheets of paper, or you can do that. You know where the semicolons are. You remember the syntax, because you're not going to be able to have a compiler tell you that you made an error. Also along those lines, tomorrow, when you have coding problems, if you are rushed for time or if you're very confused as to how you're supposed to write the particular thing in C, it would behoove you to write pseudocode or write comments in as well, because there's partial credit for a lot of the questions on the quiz. So you might be rushed or you might just be confused. Writing in comments or pseudocode are often ways that you can get partial credit. So don't leave something blank on the quiz. There's no penalties for putting things in. In fact, putting in pseudocode or comments is going to help the grader figure out if you actually know what you're talking about and maybe award you some partial credit for that. Also along those lines, write clearly. If we can't read what you're writing, we're not going to call you at midnight tomorrow to figure out what you wrote. We're just going to take off points. Write clearly so we can hear, we can read what you wrote. And if it says 2 sentences, don't write a paragraph. Follow the instructions, write clearly, and write in those comments or pseudocode for questions that could award partial credit. OK, let's go to factorial. So we have a function, factorial. If I were to actually write this in C, what do I need to put before the name of the function? The return type, which in this case will give an int. And then inside the curly braces, what goes inside the curly braces for a function?
Argument type.
It's arguments. So factorial will probably take an argument, probably only take one argument, and we'll say it'll take an integer called x. And again, when writing the prototype of a function or writing the function in your code before defining it, you write the data type and the name of that variable. That's the name of that variable for that function only. So you can pass like some number into this function. It'll be referred to as x internally. We have our factorial function. We need 2 things, a base case and a recursive call. What is the base case for factorial? Somebody who wrote it out and who hasn't spoken yet. What is the base case for factorial?
If n is less than 2, return 1.
If n is less than 2, return 1. I like that, because that takes care of 0 and 1. So we'll do x less than 2, return 1. If we get past 0, if we get past 1, this function will immediately return 1. If we get past some number greater than or equal to 2, we're going to have our recursive call. And so how is that going to work? Can somebody else who worked on this, who hasn't spoken yet, give me the recursive call for this function in pseudocode? If we get passed in a number x, and it's greater than 2, what do we want to do? We also have an example written on the side that might give you a hint.
X times the factorial of x minus 1.
Exactly right. We're going to return x times the factorial of x minus 1. And that, even though I wrote up basically what you said in English, this factorial function will get called again. It'll execute on x minus 1. It'll return with some integer, and then it'll multiply these two together, and that value will be returned to whatever called this factorial function, which might be another instance of this factorial function. So that is an example of a recursive function, a very simple recursive function, but most of them will be like this. If you would like a good recursive challenge before the quiz, try coding binary search recursively. Because if you did binary search for problem set 3, you probably did it iteratively in a while loop. But it can also be written recursively. You're going to need to write your own separate function that takes some different command line argument, or not command line arguments, some different just regular arguments. But you can write binary search recursively as well.
So like you could have also written, instead of x minus 1, you could have also written like x minus minus, or you could have written like minus minus x. Can you go in can you just explain really quickly why those like would be different things? Like what the difference is between x minus minus and minus minus x?
No, I'm not going to go into that.
Okay.
But I will talk to you about it after class.
Got it, okay.
X minus 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 x, decrement x by 1. Yeah. But they do it a bit differently,
right.
But I don't want to go into that.
Yeah, that's fine. Okay.
Other questions about recursion, or this function? That's not really even pseudocode. That's basically the code in C you would write for this. OK, any other questions about topics up here? Yeah?
We have a quick rundown of floating point imprecision.
Floating point imprecision. Can somebody really quickly give me a rundown of floating point imprecision? You all had to do this for your problem set, so you're all familiar with it. Or maybe not all of you. Anyone? Give me a starting spot. Floating point imprecision. What's the problem? Yes, Victoria? Vanessa, sorry.
There's only a finite number of integers or of numbers that can be represented because you're on in our case, a 32-bit system. So you can't. You're going to have to make up some numbers.
So that's exactly right. There are only a certain amount of numbers that can be represented. You can sometimes, if you multiply two very large numbers, it might overflow the amount of spaces you have to represent an integer. That's why sometimes we use a long instead of an int. That has more spaces that can hold a larger number. Floating point imprecision has to do with that, but also has to deal with the fact that decimal numbers are not always represented. Sorry, let me put this back up. The decimal number 1.0 is not always represented like you would expect. 1.000000000. It is sometimes represented as 1.000000001 or 0.999999999, maybe even like 89 thrown in there somewhere. So numbers, those decimal numbers aren't represented exactly like you would expect them to be represented. So in problem set 3, was it 2? Problem set 2, where we dealt with floating point numbers when we wanted them to represent exactly what we wanted them to represent, the number of pennies or the number of cents. We multiplied them by 100, we rounded them, and then we cut off everything behind the decimal point. That was to ensure that they would actually equal exactly what we wanted them to equal. Because when you when you take something that's a float and turn it into an int, you cut off everything to the right of the decimal point. Because there's some floating point imprecision, 100.000 might be represented as 99.999999999. And if you just cut off everything to the right away, you're going to get the wrong number. Yeah?
Question about casting. Like, what order does it occur in? Like, if you do float 1 divided by 10, right? Like float brackets 1 divided by 10. Does it do 1 divided by 10, then get 0.1, then turn it into a float?
if you do float 1 divided by 10.
Yeah, and then equals, well, it would normally have equal like in, yeah, you wanted to make it a float, right?
Okay, so we're going to use that to segue into figuring out the answers to these questions through coding. Because you will probably have a lot of these minute questions, and a good way to solve them is through coding. So we're going to code this right now, and then we're going to go back and code the question you had. So the first line, I shouldn't have written it. What is the first thing we want to do? We open up a new file in gedit. Include what?
CS50 library.
Okay. What else do we include?
What are we coding right now?
We're just going to check what happens when you cast something to a float. But what do we need to include if we're going to write a C program? Standard.io.h. We actually don't need for this program CS50.h, even though it's always helpful to include it. But we do always need standard.io.h.
When coding in C?
When coding in C. So I save it as this .c file. I get some nice syntax highlighting. I wrote main inside void. Or void inside main, rather. What does void mean?
Doesn't take any command line arguments.
Void means, in this case, main doesn't take any command line arguments. In other cases, it means the function doesn't take command line arguments, or the function, if I were to write void main void, that would say main's not returning anything. So void just means nothing. What would I write if I were to take command line arguments? Int argc string argv. Is that right?
Where's char star argv brackets?
So you could write string argv brackets or char star argv brackets, but you need the brackets because argv is an array of strings. Remember, it's not just one string. So string argv is, here's one string called argv. String argv brackets is, here's an array of strings. So int argc string argv brackets would be something that I would probably write. So you wanted to, what did you want? You wanted to save in an integer?
Yeah, integer, or like in a float.
In a float?
Like float x equals like 1 divided by 10.
Okay. How do I print out a float in printf? What? Percent f. What's an integer? D or I. What's a string? S. How do I get a new line? What do I return if main runs correctly?
0.
Do I need to write that line though?
Yeah.
Okay, we won't write it then. Can everybody read that? It looks a bit small. Can everybody see, or should I make it bigger? Okay. I think for the camera, we'll make it a bit bigger, though. If I want to turn this .c file into an executable, what do I write?
Make test.
Sorry?
Make test.
Make test. We saw, we were talking about this line earlier. Clang. What's Clang? The name of the compiler. What's this line?
Sets it up for use of GDB.
Sets it up for use of GDB. This line, what's that? That's the source file, the .c file. What do these two lines do? Or these two, not lines.
It names
It renames it.
So the -o says name it something differently, and here you're calling it test. If I didn't have that in, what would it name this? A.out. What does this do?
Links the math library.
It links in the math library. We didn't include the math library, but since that's so common, they've written make to always include the math library. And likewise, this includes the CS50 library. Okay, so if we list, we now have something, an executable called test. To execute it, I write test. I see my floating point as expected equals 0. Does that it? So
And then if you put float, no, like you cast it as float.
cast this, the 1 to a float?
No, class the whole thing. I mean, like if you just did that, what would that make it 0.1?
Okay, so let's go really quickly. 1 divided by 10, those are integers being divided. So when you divide integers, there's 0, and then you're saving that 0 in a float because the slash is just integer division. So now we're turning something into a float. Let's see what happens. Oops. We'll make test. So now we see that that slash was not integer division. It was floating point division because one of its arguments had been cast to a float. So now it was saying treat this division like we're dealing with floating points, not with integers. And so we get the answer we expect. Let's see what happens. Oops. How do you print? If I wanted to print more decimal spots, how could I do that?
Point dot. Yep. Whatever number. As many decimal places as you want.
So I print 10 decimal spots, and we now see we're getting some weird stuff. And that goes back to your question about floating point imprecision. There's weird stuff stored in here. OK. Does that answer your question? What else do you want to code quickly?
Oh, I just wanted to see whether or not if you freed up some pointer, whether that pointer still had stored in it the address of what it had been pointing to previously.
OK, so let's do that. Char star pointer, this creates a variable called pointer of type char star. How do I write malloc, Alden?
Just malloc, and then, but then it has to be size of, and in this case, I guess you'd be pointing to char, so it'd be char.
OK, so more generically, inside, let's edit. More inside malloc, you want the number of bytes on the heap. Generally, what we've seen that we're doing is we're going to malloc strings, for example, or arrays of integers. So if we want 10 integers, or 10 chars, 10, give us 10, and then size of chars, it'll give us that size of chars, which in this case is 1 byte. We get 10 bytes. If we were to write size of int, that would give us 40 bytes. So more generically, inside malloc goes the number of bytes you want. In this case, we're getting 1 byte, which seems like a weird use of malloc, but for our purposes, makes sense. So there's that. We're going to call free. We get rid of it, and we use pointer again. And what did you want to check?
I just wanted to check whether or not there was anything inside of it.
So whether it pointed to anything?
Yeah, exactly. Whether it still had a memory address. Yeah.
So if we wanted to, you want to check the value of pointer?
Yeah, exactly.
What do I write here if I want to check the value of the point? What is stored inside the value? Or what is stored inside of pointer? A memory address.
Yeah.
So if I write just this, that'll give me the value of pointer. And how do I print out a memory address? What's the format string for a memory address?
%s. %p.
It's %p. %s is a string. %p for pointer.
So if you do %s, show what the thing was
size of.
Is that right?
Yes.
That is right. Okay, so pointer equals, it still has some thing in it. What happens, this is probably a more interesting question. What does that line do? What?
I think it's segfaults.
I
think it's segfault.
So this line of code, star pointer, what does the star mean?
Content of?
Yeah, go to, get the content of. So this is going to go to the memory address there and give me that. I use %c right here because their character is stored there. So we're going to go to that address we just saw, or it'll probably be a little bit different this time we run the program. But we'll go to that address, which we know still exists, and see what's there. So it didn't segfault, just didn't give us anything. It might have actually given us something, we just can't see it. And that goes back to this idea, and we're not going to get too much into this because that's beyond the scope of this course. But when we talked about right here, if we went beyond the bounds of the array by 1, we might not get in trouble. Sometimes when you just go off by 1, you're doing something wrong and you could get in trouble, but you don't always get in trouble. It depends how much of a bad thing you do if you're going to get in trouble. Which isn't to say be sloppy with your code, but it is to say the program won't always quit, even if you go somewhere you're not supposed to go. A good example of that is a lot of people in their problem set 3, which was 15, did not check the bounds of the board. So you would look to the left, look to the right, look to the top, look to the bottom, but you didn't check to see if the top was actually going beyond the board. And a lot of people who did that and turned that in, their program worked perfectly, because where that board was stored in memory, if you went one above it or checked that memory address, there wasn't anything particularly horrible about that, so your program wasn't going to yell at you. But we would still take off points if you didn't check that, because you were doing something you weren't supposed to do, and you could have gotten in trouble. Odds are, though, you probably didn't. So this is to show that, yes, we can still go to it, and we're not getting in trouble in this case. If we tried to do read the next 100 characters, we'd probably get in trouble. And you can code reading the next 100 characters if you want by doing some sort of for loop. Yeah?
Since we never assigned that space an actual value, like we wouldn't actually be able to see anything, should we like try it with setting that equal to like C or something?
Great question. How do I set that value? What line of code do I write on line 7 to do what you said?
Star pointer equals single quote C and single quote.
So that's putting a character, C, at that location, because again, that star means go to there. And when used on the left-hand side of an assignment operator, that equal sign, we're not going to get that value so much as set that value. Now let's see what happens. We put something there, and it was there. We called free. Some stuff probably happened on the heap, so it's not there anymore. But again, we're not getting in trouble for going there. I'm doing this out in code to illustrate that a lot of these questions that you have, they're really interesting answers a lot of the time, and they're really good questions, and you can figure them out on your own if, for example, we're not in section. Yeah?
Because you're not sending a pointer anywhere, do you need to use malloc?
So this goes back to your initial question. Yeah. This is just a local variable. Malloc here is not that compelling. Yeah, the use of malloc here is not that compelling because it's just a local variable.
So could you do like char star pointer equals like hello? Like.
Oh, so we're going to now get back to your initial question that you weren't satisfied with my answer. Okay? Like that?
Yeah.
Wait, you have to take up this. Yeah.
And what do you want to print out?
Yeah,
the value.
So we'll print out a string like that.
Interesting.
So this says this argument has the type of a character. So this should be a character.
It just takes the first one.
So this is what I said before, right? Like I said, it's not storing the string inside the point. It's not storing the string inside that variable pointer. It's storing
the first value of the string.
The address of the first value of the string.
Yeah. Okay.
Right? If we were to print out this, we're getting the value inside pointer, and we'll see it is indeed a memory address.
Yeah.
Does that make sense? Sorry? Wait, does that answer your question, though?
Yeah.
This line of code is creating a string, and then another variable pointer that's pointing to that string, that array. Yeah?
So if we went one memory address further, would we get the H? Like, has it been stored as
like if we did... So this is valuable to do. This is point arithmetic, which you guys have seen before and should be relatively comfortable with. This is akin to writing if we were to write this line of code, we've seen array notation before. This should give us the second value in this array. H.
Okay, got it.
If we did this, this should also give us the second value in that array, because it is going not to the memory address of the first thing, but the memory address of the thing 1 over, and then the star operator dereferences that pointer. And again, let's see, we get H again.
What exactly does dereference mean?
Dereference is a fancy word for go to. Go to that and get what's there is to dereference a pointer. It's just a fancy word for that.
If we wanted to print the whole string, could we do like ampersand pointer?
Okay, we're going to pause here. We're going to end here. Ampersand gives you the address of a location. So when you do ampersand of a variable, it gives you the address where that variable is stored. Ampersand pointer will give you the address of pointer, where pointer is in memory. We're not going to go on with this example. You can figure out these things on your own. But again, this might even be verging a bit beyond what you need to know for the scope of this midterm, or this quiz rather, sorry. We are going to move on, because I would like to do one coding problem before time is up. And we are going to code what I think is the most compelling of these examples, A to I. So this was a question on a quiz 2 years ago. And I have it on the board here. People were asked on the quiz. There was given a little more text in the question, but I eliminated the text because it was unnecessary for our purposes now. There was just some background on what A to I did. But you all know and are very familiar with A to I. I suggest you code this on a sheet of paper. I also suggest you use the strategy that we've gone over a lot in our section. First, make sure you understand what A to I is doing. Draw a picture or come up with some mental image of it in your head. Next, write out pseudocode for this. On the quiz, if all you get is pseudocode, at least you put something down. And then map that pseudocode onto C. If you have a check in your pseudocode, like check if something is 1, that maps onto an if condition, and so forth. And finally, code the program in C. So I'll go back to A to I and take 5 minutes to code this on a sheet of paper, which is probably about the amount of time you would take on a quiz to code A to I. 5 to 15 minutes. 5 to 12, 5 to 10 minutes is about the amount of time you'd spend on this question in the quiz. So take 5 minutes now, please. And if you have any questions, raise your hand, and I'll come around.
every like.
Go back to this. Okay, so that was 5 minutes. That was probably about the amount of time you'd spend on that on a quiz, maybe the low end of that time. We'll recap in a bit. Let us start coding this. And if we don't get all the way through, the answers to this and this quiz question are available again. Fall 2011 is when this question appeared on the quiz. And it was worth 8 points on the quiz then. 8 points is on the high end of the amount of points something is worth. Most questions are in the range of 1 to 6 points. So this is a more challenging question for sure. Ada, can anybody get me started? Or generally, what are we going to want to do with this function 8i? Logically, what do we want to do? So we're going to write some pseudocode.
Convert characters into integers.
Convert characters into integers. Okay, so how many characters are we going to need to go through?
All of them?
All the characters in the string.
All of the characters in the string. So if we want to go through every character in a string, what is a thing in C we've seen that has allowed us to go through every character in a string? A for loop. So we're going to want to loop through every character in S. Then what are we going to want to do when we get a specific character? Say we're getting past a 90. We get the 9. It's a character. What do we want to do with that character 9?
Subtract it from character 0.
Add 0.
Subtract it from character 0?
Yeah.
Why do we want to do that?
So the character value. It's int value.
Okay, so we take the character 9, subtract it from character 0 to get an actual integer 9. Sweet. And how do you know that character 9 minus 0 character is 9? What chart did you look at?
They're just like logically 9 places between 9 and 0. Or you could look at the ASCII table.
ASCII table. But yes, you're correct as well. So we subtract 0. So now we have the integer 9. And what do we want to do with that? If we have 90, it's the first integer we have. What do we want to do?
I'd put it in a temporary integer array, then do math to it later to make it into an int.
Okay.
You can start at the end of the array and then move forward so that every time you move forward, you multiply it by 10.
Okay, that sounds like a pretty compelling idea. We can start at the end of our array, and we can use Sterling. We can use Sterling in here. We'll get the length of our string. We start at the end, and with the first one, we just take that integer, and maybe we create like a new integer variable up top where we're storing everything. So we loop through every char in S from back to front. We subtract 0, and then we take it, and depending on where it is, we multiply it by a power of 10. Is that, because the first one, what do we multiply the rightmost character by?
10 to the 0.
10 to the 0. What do we multiply the second rightmost character by? What?
10 to the 1.
10 to the 1. The third rightmost character?
10 to the 2.
10 to the 2.
Sorry, I don't understand what we're doing here. Like,
Okay, let's go back then. So we get passed in a string, because we're writing A to I.
Right.
So we get passed in a string, say we're getting passed in the string 90. The first thing we're going to do is set a new integer variable that we're just going to create as our new integer. That's what we're going to return at the end. We need to go through every character in the string, because we've determined that we need to touch each one and then add it to our new integer. But we can't just add it as a number. We can't just take 9 and add 9 to our integer. It depends on what place it is in the string. We are going to need to multiply it by a power of 10, because that's how base 10 works.
Okay.
So we're going to get the actual character, or the actual integer number, by subtracting character 0 from character 9, like we did with subtracting character capital A from whatever character we had in one of those problem sets. We'll actually get a number from 0 to 9, saved as an integer, or saved as a real number, and we'll multiply it by a power of 10 depending on where we are in the string. And then we will we're going to add it back into our new integer variable. So what this would look like would be, we'll draw over here, if we get passed in the string 90, so we get, but A to I takes a string.
Right.
So we're going to go through the whole thing. We'll get passed in 90. We go from the back to the front. We take the 0.
But if I'm sorry, maybe this is stupid. If we're getting passed in a string, why is 90 what we're getting passed in? Because 90 is an integer. I think it's 9 is an
Okay,
integer.
because A to I takes a string and turns it into its integer representation of that string. But the string 90 is not the integer 90, or the number 90.
Okay.
The string 90 is an array of 2 or 3 characters, rather. The 9 character, the 0 character, and the \0 character.
Okay.
And we're writing A to I because, for example, when you take a command line argument and it's saved in argv, it's saved as a string. But if you want to treat it as a number, you need to convert it to an actual integer,
Right.
which we did in one of our problem sets, which we did in a number of our problem sets, everyone that took an integer as a command line argument. So that's why our A to I function takes a string.
Okay.
So again, in our example here, we're going to take the last one. We're going to subtract the character 0 from it, because the character 0 subtracted by the character 0 gives you the actual number 0, according to the ASCII math that we do, because characters are represented as different than their actual. The character A, for example, lowercase a is 97. It's not whatever you would expect it to be 0, for example. So you have to subtract the character A to get 0. So we're going to do that here to get the actual number. And then we are going to multiply it by a power of 10, depending on where it is in the string. And then take that and add it to our placeholder variable. So we can come up with our final new integer. Does that make sense to everyone? So we're not going to code this right now because we're getting short on time. I apologize for the timing of that. But this is what hopefully you would be able to do on the quiz. At the very least, get this pseudocode written out. And then if we were to write the pseudocode, actually we could do this pretty quickly. Each line of comments we wrote here translates to about 1 line of C code. Declaring a new variable, writing a loop, some subtraction, some multiplication, and some assignment. We probably also want to write a return line. We might also want to put some checks in here. Yeah.
So can we treat S as the actual string? Because I know it's just an address. Like, how would you get the length of the string being passed in?
So how do you get the length of a string?
String use string length. But
Strlen,
yeah. But can you put S as the argument for that?
So Strlen takes a char star.
Oh,
and it follows that char star and it goes until it keeps counting until it gets to a \0. Stirlen was actually one of the other programs we were going to code. That's another good one to code. That one's a bit easier because if you're going to think about that conceptually, I just said it out loud. Stirlen follows a pointer and keeps going and counting and keeping track until you reach a \0.
Okay, got it.
So best of luck on Quiz Zero tomorrow. If you have any questions, I'll be outside after this. Feel free to email me. Reach out to your own TF if you're not in my section, or get my email if you want it. If you want to freak out and just send me an email, a freak out email, I'll send you back like a smiley face or like a joke or something, so feel free to do that as well. Good luck again, and I'll see you all next week.